to work with y instead of x. So for example, if x is uniform AB, we can transform x into the standard uniform, and so since all the probability lies between A and B for x, all the probability will lie between 0 and 1 for u, so that's why it necessarily integrates to 1. So the expectation invariance we also saw last time. So today we're going to review the concept test responses from last time, section 4.1 on change of scale calculations, and we'll briefly introduce the CDF as well as start section 4.2 on the exponential distribution. So remember the concept test from last time. Suppose a manufacturing process designed to produce rods of length 1 inch exactly, in fact produces rods with length distributed according to the density graphed below. So this density here, to be a density, it must have height 10. And basically the question is, which change of scale do we want so that the density is going to be as nice as possible? So let's just take a look at some different student responses here. So these are the different densities that these students considered, and you can see that the last one, the one in yellow, is the simplest. So we need a change of scale that will do this for us, and so we need to change the range of values from between 0.9 and 1.1 to between -1 and 1. And to do this, we need to translate to the origin and then spread out the data so that it's between -1 and 1. And so that's 10 times parenthesis x minus 1. The height of the density, the height of the density in the middle there is determined because, again, we necessarily have area 1. So here's some more change of scale. Here's another change of scale calculation. So suppose that in this problem that we were considering, we want to find the variance of the length of the rods. So it's going to be much easier to find the variance of y than to find the variance of x. And the variance of x is the variance of y over 100. So let's just find the variance of y. So again, y has the distribution shown here, and so the variance of y is expectation of y squared minus expectation of y quantity squared. The expectation of y is 0, since it's centered at 0. So again, that's one reason that it's nice to work with y. And then we also notice that this distribution is symmetric around the vertical axis, so it's called an even function. And so the expectation of y squared is just twice the integral from 0 to 1 of y squared times the density minus y plus 1, which is 1/6. So then the variance of x is 1 over 600. So let's just quickly see what the CDF is. So the CDF is the probability that x is less than x. In other words, it's the integral from -infinity to x of f of x dx. So for example, if u is uniform 0, 1 with density 1 or 0, namely 1 between 0 and 1, then the CDF, so the CDF, the only calculation you really need to make is is for the when the density is between 0 and 1, and in that case we're going to integrate from 0 to u 1 dx, since the density is 1 between 0 and u. So so we get fu is equal to u. So that's just a diagonal line. So between 0 and 1 we get a diagonal line. Before 0 there is no probability in our density, right? There's no area. So so f of u is 0 there, and after 1 the density is 0, so we're not going to get any more probability after 1, so it'll just stay at 1. So f of u takes three values, 0, u, and 1. It's 0 up to 0. For u up to 0, it's u between 0 and 1, and it's 1 after 1. And if you take the derivative of the CDF, you just get the density. That's the fundamental theorem of calculus. And so the density and the CDF are equivalent ways to describe random variables. So now finally we come to the exponential and gamma distribution in section 4.2. We'll just talk about the exponential distribution today. So we start with what's called the memoryless property. And the memoryless property is something that the geometric distribution has, and since we're familiar with geometric, let's start with that. So this will be our motivation for looking at the exponential. So if x is geometric p, x is the number of trials until you first succeed. So we have the geometric formula, and you can easily see that the probability that x is greater than k is q to the k. So if x is geometric, then probability that x is greater than k is q to the k. Conversely, suppose you don't know that x is geometric, but you're told that the probability that x is greater than k, the probability that x is greater than k is q to the k. Well, we can write probability that x is k in terms of the probability that x is greater than k minus 1 minus the probability that x is greater than k. And using our formula, we see that we get the geometric formula. So probability that x is greater than k equals q to the k implies that x is geometric. We get the geometric formula. So x is geometric p if and only if probability x is greater than k is q to the k. So now question, if it takes you more than 10 j equals 10 p coin tosses to get your first heads, what's the chance it'll take you more than k plus j equals 13 coin tosses to get your first heads? So you've already flipped the coin 10 times, haven't gotten the heads, and so basically what's the chance that you don't get a head for the next 3? Well, isn't it obvious that it'll be at least isn't it obvious that it is the probability, the unconditional probability that x is greater than 3, because what you got in your first 10 tosses doesn't affect what you get after your 10 tosses, because each toss is independent. So in other words, we should get q cubed. And so what I'm saying here is that the conditional probability x greater than k plus j condition on x greater than j is equal to the probability that x is greater than k. So that is the memoryless property of geometric. And the interesting thing is that geometric distribution is the only discrete distribution with values 1, 2, 3, and so on having the memoryless property. So to prove this, we'll show that the implication goes both ways. So first we're going to assume that X is geometric and show that we have the memberless property. Then we'll show we have the memberless, if we have the memberless property, that we're geometric. So if X is geometric, then probably that the conditional probability you can find using Bayes' rule, which you can easily see as Q to the K, which is probably that X is greater than K. So that shows the memberless property. Now conversely, for positive integers K and J, suppose you have the memberless property, so that gives you this equality that the probability that X is greater than K plus J is equal to the probability X greater than J times the probability that X is greater than K. So now if so we need to show that this equality implies that X is geometric. So we're going to define Q to be probability that X is greater than 1, and we're going to show that the probability that X is greater than J is Q to the J, right? That if we show that, that will show that X is geometric. So you're going to pull out your mathematical induction muscles, and we're going to check the base case. Great. We're going to assume that the probability that X is greater than J minus 1 is Q to the J minus 1. And now we'll finish the proof, the inductive step. So we're going to write the probability that X is greater than J. We're going to write this as probability that X is greater than J minus 1 plus 1, which is the probability that X is greater than J minus 1 times probability that X is greater than 1. And that gives you Q to the J. So X is geometric P. So only two distributions are memberless. For discrete x1, x2, x equals 1, 2, 3, and so on, we have geometric. And for continuous t greater than 0, we have exponential. And the proof is very similar to geometric. So the exponential distribution is as follows. T is exponential if t has density f of t lambda e to the minus lambda t for t greater than or equal to 0. It has this graph here. So t, for example, is the time till your first success, where lambda is the rate of success, or t is the time until a light bulb burns out. And we can find the CDF and survival function very easily. So the CDF is just a calculation, and then the survival function is defined as 1 minus the CDF, or in other words, the probability that t is greater than k. It's called a survival function because if you think of success as death, is probability that t is greater than t means that you're surviving at least till times t. So that's decreasing exponential, unfortunately. So now, we see that t being exponential lambda is if and only if the survival function is e to the minus lambda t. So this is a characterization of exponential that we'll use often. Finally, I just want to finish and note that exponential is a limit of geometric. In particular, if x is geometric p and px is a change of scale of x, then we'll show that px, that discrete random variable, converges to exponential 1. So lambda equals 1 as p goes to 0. To see this, note that px takes values p, 2p, 3p, and so on, since x is geometric. And so the probability that px takes these values is p, qp, q squared, p, and so on. And if you just graph that probability mass function and you make p really small, you'll see that you get an approximation of exactly the exponential 1 distribution. The vertical intercept there is 1, lambda equals 1. Great. So have a great day, and I'll see you next time.